Joe. Joe, we're close to a revolution here.
Martin, I love the terminology you use. It's totally awesome.
Okay, so you talked to us about test-driven development. Please explain that.
So test-driven development, we ported it from software to hardware, and here's what we mean by it in hardware. So we call it test-driven manufacturing. We start with a test fixture before we build anything. So we start with a user story. As Joe, I can drive a car that gets 100 miles per gallon so that I can improve the environment of the world I live in. So now we have a goal to hit. Now we need to make a test to know if we passed that goal or not. So we get a set of dyno rollers and an emissions collector and a fuel flow meter so we can go through the EPA City and Highway Driving Cycle and know our fuel economy. We haven't built a car yet. We've gotten access to that test fixture before we built anything. So we start with a failing test. That way it focuses all work directly on making the slimmest thing, the quickest thing that will pass that test.
Failing test?
Yeah, we start with a failing test fixture. The ability to measure, do we have a 100 mile per gallon car? But we haven't built a car yet.
Yeah,
We've acquired access to the test fixture. We built the test fixture. And it's our job to be able to repeat that test as cheaply in terms of time and money as possible so we can run that test hundreds of times during our development cycle to know if we passed it yet and know if we're improving. So it gives us laser focus on the end goal, and it avoids gold plating or building more than we need. So we start with the failing test. Now we build the product. Once we've built the module, say it's an engine module, we then unit test it. So a test fixture for an engine module for us is an accelerator pedal, a fuel gauge, and a shifter all by itself. So outside of a car, you plug it into the engine module sitting on a test fixture, and you accelerate it, and you shift its gear, and you monitor its fuel level consumption. You haven't even put it in a car yet, so that's unit testing. Then we do integration testing. We put it in the car, and we verify it still works in the car. Then we do regression testing, which is we run every test we've ever built on the car again. We make sure that the headlights still work, it still turns, the brakes still work, the horn still honks, so that that new module we introduced didn't just regress anything, it didn't just break anything. So those are our 3 levels of testing. So test-driven development gives us focus, and it helps laser focus the team on just passing the test, which is your valuable thing. And then unit testing determines is that module successful, and then we have integration testing. Does it work as part of this larger structure? And then we have regression testing, which is does introducing that new work move us backwards anywhere else? And if so, we then get to kill work early. It also helps us identify any work that's not being done to pass a test. So it helps identify work that's not actually adding value to the project, to help redirect it and coach those people to be excited about something that will work on passing a test. So it's easy to say, hey, that thing you're doing, which test is that trying to pass? And help direct that work into something that's going to have dramatic value for us soon. And we know exactly when it's worked or not. There's no guesswork because we have a test fixture, and that drives morale. That's what helps cement the reality of regular successes, because you have these test fixtures that don't have any question about whether you've just made real forward progress or not.
And how do you test for things that are not immediately visible, such as longevity of parts?
You would have accelerated stress testing. So longevity of parts, you'd have accelerated stress testing, or you'd make the part in miniature so that the failure would happen an order of magnitude faster. But in my world, I'll think about the things that we would care about the longevity of. We do finite element analysis, and so it's a simulated structural fail. So you say, here's the finite element analysis of applying this force over these vectors over this many repetitions. Now we need to develop something in CAD that passes those tests without having decreased structural properties. So we create that test first.
Does FEA typically yield the correct results, or how useful has FEA turned out to be?
It completely depends on the program. There are programs such as LS-DYNA that have achieved complete correlation with physical crash test results, for example, in crash testing. What they do is they take a coupon of a material and they crush it in slow motion, and then they run the same test on a coupon in finite element analysis and verify they deform exactly the same way. And once they build up a battery of different materials, they have high correlation between the two. LS-DYNA has done that for things like entire cars at a time. It's very refined. Now, it's an expensive piece of software, but there's a free 30-day trial, so we can work with it free 30 days at a time. And they may end up sponsoring us with a license. We'll see. But correlation is what enables the software to give meaningful feedback on the real world, and not every FEA software has any correlation. So there's some types of problems, like maybe a piece of FEA software has high correlation with tubes that are aluminum or certain grades of steel, but has no correlation of carbon composite tubes or square shapes. And so it helps to understand what the finite element analysis software is built to do, to make sure you're using it for something it has high correlation on.
Okay. Excellent. This is test-driven development. We're going to have to apply that to more of our techniques at the Global Village construction set.
From extreme programming, which is now ported to the physical world because there's some value in it.
High five.